for this video, we are going to discuss how to implement multiple linear regression using these squares in Python. So we have this equation that represents a linear model with multiple na predictors. So we have x sub 1, x sub 2 until k na predictor. And then each of the predictors will have an associated na weights or model parameter. Okay, so we can express it in a matrix notation form with y equals x times the model parameter or the beta parameters plus the epsilon or the error. Okay, so the y is a vector of n by 1 na responses, and then we also have the x composing of x na predictors with n samples. Okay, and we note that we have added a 1 or an extra column composing of all ones. And then we have the beta na parameters, which is, as you can see, multiplied to each of the predictors. Okay, the beta 0 is the intercept or the bias, and then the rest are the coefficients of each na predictor. Okay, and then of course each will have an associated na error. Okay, so first we have to load our data set. So as you can see, we simply use a pandas data set to load this. Okay, and now we are going to prepare our data. So first is we are going to extract only the X na values, and we only need TV, radio, and newspaper. So we will drop the sales. Okay, and then we are going to insert another column here such that it contains all ones. Okay, and then the Y on the other hand contains the responses, which is the column na sales. So let us try to see what X. As you can see, there is an added column composing of ones. Okay, next we have to prepare our data set. So we have to divide the data into train and test set. Let's say 25% is allocated for the test set and the rest will be for the train set. Okay, so we have here, and then let's say printing the shape of X train. We have 150, and for the X test, we have 50. Okay, and now after which we have to fit a line on the train set. Okay, and we will use that fitted na model to predict the test set. Okay, so we will be estimating this beta parameters from the train set. Okay, so let's see. We have the beta, say, is equal to the dot product of X transpose and X. Okay, so let us visualize it one by one first. So we have the X train and its transpose, and then X train, and then we will take their dot product. And it gives us these values. And now we are going to take the inverse. So we can do it using np.linealg.inv, and we simply plug in the dot product of X and X transpose. Okay, and now after computing this, we can take the dot product of this inverse and the X transpose. So np.dot and X train transpose. Okay, and now we are going to take the dot product of this with Y or the responses. So we have np.dot, and we have the Y. Oops, and it's supposed to be y3. Okay. Okay, now we are going to store this into the beta. Okay. And the beta 0 actually is the first element of beta. Okay. And then we have the beta 1. And the rest of the elements of beta. So printing it, beta 0 and beta 1. As you can see, we have here the bias, and then the rest are the coefficients or the weights of every other predictor. Okay, now we are going to use this parameters to estimate the y or predict the y na values. In this case, we have the predicting the sales from the TV, radio, newspaper na inputs. Okay, and as well as the estimated na beta parameters. So we can do that using NumPy. So first is that, as you can see, let us visualize our y-test first. So we are already done, by the way, fitting or estimating, and we estimated this from the train set. So we are going to predict y from the test set. Okay, test set. Now, visualizing y-test. So we have this list of responses. Okay, and we want to predict y hat or the future na sales. Okay, and what we can do is to this y, we will be multiplying the beta with each of the predictor. So we have here the X test, right? And we have listed here each of the column. And then each of this, let's say one column, will be multiplied with the estimated na beta parameters. So for example, sales 96. What we are gonna have is that the B0 plus B1 times TV for 96, and then plus B2 for radio times 96, radio 96, plus B3 times radio, newspaper 96. Okay, so that's how you can visualize it. So what we are gonna do is to perform multiplication. Each row, we will multiply X train or X test with the beta. And see, it is changed now. And of course, we have to predict the response, and we have to add these results. Okay, so we have np.sum, and then we have y hat. And now we have the predicted na values. Oops, we have to add axis is equal to 1. So it will add the rows. So going back, in order for us to estimate y, we have to add each of the rows. Okay, so that's why we have added axis equals 1. Now we have to evaluate whether the y hat is good enough. So we can do that by computing the error and the residuals. So the error is simply computed from the difference between the actual and the predicted. And then we take the square of these errors and take the sum. And it can also be computed by computing for the errors and then having a vector of errors, and then taking the dot product with its transpose. So in other words, we have let's compute for the error first. Suppose we have the error. So y hat minus y test, okay? And we have here the errors, and we will take the square of these errors. Okay, and we have that, the squares of these errors. And taking the sum, so that is the RSS, okay? And then in order for us to solve for the MSE, so the RSS divided by the length or the number of samples in the y na test. So then of y test, so that will give us the MSE. Alternatively, we can solve that by multiplying the error vector or taking the dot product of the error vector by its transpose. So we have the error and then error transpose. Then we'll take their dot product. And we will, this is, as you can see, equivalent to the RSS earlier. And in order for us to get the MSE, so we simply have to solve divide RSS with the len of y test. And we have the MSE. So as you can see, it produces the same results, okay?